The National Electrical Code, or NEC, began requiring three-wire systems with a common ground in homes in 1962. Prior to this, older two-wire systems without a dedicated ground wire were common. The introduction of the three-wire system with a ground wire marked a significant advancement in electrical safety. In a two-wire system, there are typically two conductors, a hot or phase wire and a neutral wire. The hot wire carries the electrical current to the device, and the neutral wire provides a return path for the current to the source. In such a system, if a fault occurs, such as a short circuit where a hot wire comes into contact with a metal enclosure, there is no dedicated path for the fault current to flow back to the source and trip a circuit breaker. This can leave the metal enclosure energized, posing a shock hazard to anyone who comes into contact with it. The three-wire system addresses this safety concern by adding a third wire, the ground wire. This ground wire provides a low impedance path for fault current to flow back to the source. When a fault occurs in a three-wire system, the fault current flows through the ground wire, quickly tripping the circuit breaker and disconnecting the power. This significantly reduces the risk of electric shock. The ground wire is typically connected to the metal enclosure of appliances and equipment, ensuring that if a fault occurs, the enclosure is immediately grounded, preventing it from becoming energized. The NEC adoption of the three-wire system with the ground wire in 1962 was a major step towards improving electrical safety in homes. This requirement has been continuously updated and refined in subsequent editions of the NEC to further enhance safety and address new technologies and wiring methods. The grounding system is a critical component of any electrical installation. It's designed to protect people and property from electrical shock and fire hazards. A properly installed and maintained grounding system provides a low impedance path for fault currents, ensuring that circuit breakers trip quickly and safely, disconnecting the power and preventing dangerous conditions. The NEC specifies the requirements for grounding systems, including the size and type of grounding conductors, the methods for connecting grounding conductors to equipment and enclosures, and the requirements for grounding electrodes. Grounding electrodes are typically metal rods, pipes, or plates that are buried in the earth and connected to the grounding system. These electrodes provide a direct connection to the earth, helping to stabilize the voltage of the electrical system and provide a path for fault currents to dissipate. The NEC also requires that all metal enclosures of electrical equipment, such as circuit breaker panels, junction boxes, and lighting fixtures, be grounded. This ensures that if a fault occurs, the enclosure will be immediately grounded, preventing it from becoming energized and posing a shock hazard. There are different types of grounding systems, each with its own advantages and disadvantages. The most common type of grounding system is the grounded system, in which the neutral conductor of the electrical system is connected to ground. This type of system is widely used in residential and commercial buildings. Another type of grounding system is the ungrounded system, in which the neutral conductor is not connected to ground. This type of system is typically used in industrial applications where a high degree of reliability is required. Ungrounded systems can provide a higher level of immunity to ground faults, but they also require more sophisticated monitoring and protection devices. The NEC also addresses the requirements for equipment grounding. Equipment grounding is the process of connecting the metal enclosures of electrical equipment to the grounding system. This is typically done using a green or bare copper wire that runs from the equipment to the grounding system. Equipment grounding is essential for preventing electric shock hazards. If a fault occurs inside a piece of equipment, the fault current will flow through the equipment grounding conductor, quickly tripping the circuit breaker and disconnecting the power. The NEC also specifies the requirements for bonding. Bonding is the process of connecting different metal parts of an electrical system together to create a low impedance path for fault currents. Bonding is important for ensuring that all metal parts of the electrical system are at the same potential, reducing the risk of electric shock. The NEC also addresses the requirements for surge protection. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges such as those caused by lightning strikes or power grid disturbances. SPD work by diverting the surge current to ground, preventing it from damaging sensitive electronic equipment. The NEC requires that SPD be installed in certain locations, such as at the service entrance of a building. The type of grounding system used can also affect the performance of SPD. A properly grounded system provides a low impedance path for surge currents, allowing the SPD to effectively divert the surge to ground. The evolution of grounding requirements in the NEC reflects a continuous effort to improve electrical safety. From the initial introduction of the three-wire system with a ground wire to the more recent requirements for arc fault circuit interrupters, or FSIs, and ground fault circuit interrupters, or GFCIs, the NEC has consistently adapted to address new hazards and technologies. FSIs are designed to detect arc faults, which are a common cause of electrical fires. FSIs work by monitoring the current flow in a circuit and detecting abnormal patterns that indicate an arc fault. When an arc fault is detected, the FSI quickly trips the circuit breaker, disconnecting the power and preventing a fire. GFCIs are designed to protect people from electric shock hazards. GFCIs work by monitoring the current flow in a circuit and detecting any leakage current to ground. If a leakage current is detected, the GFCI quickly trips the circuit breaker, disconnecting the power and preventing an electric shock. Grounding systems need to be inspected and tested regularly to ensure that they are functioning properly. A qualified electrician can perform a grounding system inspection to identify any potential problems such as corroded grounding conductors or loose connections. Grounding system testing involves measuring the impedance of the grounding system to ensure that it is within acceptable limits. If the grounding system impedance is too high, it may not provide an adequate path for fault currents, increasing the risk of electric shock. The information provided here offers a general overview of grounding requirements and should not be considered a substitute for professional advice. It is essential to consult with a qualified electrician and refer to the latest edition of the NEC for specific requirements in a particular location. The NEC is updated every 3 years, so it is important to stay current with the latest changes. Working with electricity can be dangerous, and it is essential to take all necessary precautions to protect yourself from electric shock. Always de-energize circuits before working on them, and use appropriate personal protective equipment such as insulated gloves and safety glasses.